Okay, so we're back, and let's talk about the emergence and re-emergence of metals and minerals, for that matter. So, man is a tool-making animal. That is for sure. That was Benjamin Franklin's quote, and maybe that's our most defining characteristic. And tools require materials, and metals are particularly important for that. So everybody sort of heard about the Stone Age, the Paleolithic age, the Mesolithic, Neolithic. It's basically how people were working with rocks. Then all of a sudden, they noticed some things that were even better than rocks. And this is just thousands of years ago. This is just yesterday. Humans have been around for 1,000,000 years, and it was only in the last few thousand that all of a sudden we started noticing, oh, copper makes a nice thing. Oh, bronze is even better. Oh, iron is even better, and then it's basically been an accelerating utilization of these different parts of the periodic table since that first interaction. It's a remarkable evolution in human history that's often forgotten as we try and understand how we got to where we are today. Now, so the geology and the use of ores by early civilizations has been benefited by the fact that these metals show up in different ways relative to the Earth's surface. So many ores, not all of them, as you'll learn, are originally sulfide ores. And sulfide ores, as you'll learn, cause particular challenges for refining to be used. What early humans wanted was native metals, things they could pick up and just hammer and turn into what they wanted. And gold was always good for that, but it's not very good for a tool because it's not very hard. It doesn't hold its shape well. Better for other uses. But things like copper, which were harder, were very useful. But to use them, humans had to be able to encounter them first as their native element. And that would occur in some cases near the surface, in what's called the zone of leaching, where rainwater and groundwater biological activities interact, and sometimes to make pure metal nuggets lying on the surface. Now, people, once they got clued into the fact that copper metal was useful, they quickly used it all up and were left with something underneath it, which was not native metal. It was not copper metal. It was pretty. It was, the beautiful oxides and hydroxides and carbonates of copper are big collector's items, malachite, azurite, bornite, all of these minerals that are very popular at mineral shows. So they had to be able to figure out a way to get the metal out of the oxidized material, and then move on down the section from that. So the beginning of the Metal Age was beginning to use these native metals that were lying on the surface in certain places. So in the evolution of pre-iron metallurgy, we can recognize 4 stages. The first one is native metals that we've just talked about, where they were hammered and annealed, and gold, copper, and silver were the first because they could be obtained in that native state. The second stage was the reduction, smelting, melting, and casting of metals using oxide ores, where the metal is combined with an oxygen. And once that was done, the door was open to begin playing around with alloys such as bronze. The Bronze Age is a very important stage in human evolution. And then after bronze was mastered, then sulfide ores began to be attacked and processed. And that sequence there, 1, 2, 3, 4, that is a technology sequence, because there had to be advancements in a lot of understandings and technologies in order to do that. So the Copper Age, copper weapons, particularly tools and edge weapons like daggers, knives, spearheads, they were first used during the Copper Age, roughly between about 5,000 and 3,000 BC. And, metallic copper was almost miraculous. It was tough, strong, much more versatile than stone, made for great weapons, and it gave a huge advantage to the groups that mastered this technology. And with the rise of the Copper Age, it also drove market economies because all of a sudden, if one group of people had a copper deposit, they had something that they could trade with to get food or whatever else they wanted to. And with the advance in the copper technology, there was a greater emphasis on the warrior culture, especially in Europe. And this is the time when we see the first signs of massacres, battles, and warrior burials beginning with the rise of the Copper Age. So, like we said, they began by picking up native copper metal near the surface. Now, if you want to get the copper out of copper oxides, you don't just pick it up and hammer it. You've got to melt it. You've got to smelt it. And to smelt copper oxide, you got to reach temperatures of about 1235 degrees centigrade, which is the melting point of cuprite, copper oxide. And to extract copper from the oxide, you need a slightly higher temperature to reduce the oxide to a metal form. So that took some time before that was figured out. Now here's an example of a copper oxide. This is malachite. It's very complicated copper oxide. It's actually a copper carbonate hydroxide, but these are very popular rocks in the market. It contains about almost 60% copper if you can extract it. And I learned that malachite was named after this plant in Greece, the Molochites. So the earliest large-scale copper production is thought to have begun around 5,500 to 6,500 in Mesopotamia and Anatolia, and the beginning of this leaching. And let's watch see how they did it.
raczej nie, a ojciec miał tam też. Bo do przedszkola wracam, to muszę a to bardziej.
Letni Festiwal Sztuki w Szklarskiej Porębie. Zapraszamy serdecznie. Głównie świetnie warsztatowe, trochę osób już się odważyło wejść, to znaczy, że się zarejestrować w
Oj, to przekuć teraz.
Proszę Państwa, letni Festiwal Sztuki.
This brings us, once that ability to turn an oxide into a metal was worked out, people started playing around with different metals. And bronze was the solution. This is an alloy that's made of an alloy is something that's basically a solid solution made of two or more metals, or it could be a metal and a non-metal. But it's basically a mixture. Alloys are generally made by humans. And bronze was typically composed of copper and tin, typically 88% copper and 12% tin. Bronze is a better metal for weapons than copper because it's harder, more durable, holds the edge better. And people started using bronze around 3300 BCE. And you may get confused between bronze and brass. I certainly do. But bronze is a copper tin alloy, whereas brass is a copper zinc alloy. And bronze was the copper tin alloy. All right, so people started making bronze. Well, here's a 2500 BC, but it was a little bit after copper was first used. Now, we need to sort of change gears a little bit. And this is a complicated diagram. It is the periodic table of elements for the sun, which is what the Earth was made from. And this is a log scale. So it's 15 orders of magnitude. So this is a huge variation. And you'll see, because it's solar abundances, hydrogen and helium are way up there. Obviously, there's not that much of either in the Earth. But the rest of this relative proportion pertains to the Earth. So the way that people plot these things this is the abundance in the solar system, which is essentially the sun. It's log 10. So that's the number of atoms of the element per million atoms of silicon. So Si has got an abundance of, where's our set? There it is. So 10 to the 6th, right? So this is basically setting the abundance of silicon in the sun to a million, and then everything's relative to that. And what you can see is there's oodles of hydrogen and helium, and then you got this interesting dip in lithium, beryllium, and boron. And then there's quite a bit of these lighter elements, and as you get heavier and heavier, you get less and less of the elements. So, for example, we'll talk a lot about the platinum group elements like ruthenium and rhodium and palladium and things like that. They're a million times less abundant in the sun and in the Earth as silicon. Now, we've been talking about copper, which is not very abundant, but that's like 1,000 times less abundant than silicon. But iron is as abundant as silicon in the sun and in the material that went on to make the Earth. Now, iron is a complicated element, but the point of it is I want to make with this, and we'll see this diagram again in several other contexts. The point I want to make is there's a lot of it around, and even though most of it's inaccessible in the core, enough of it is in the crust to be a resource if it could be figured out how to use it. All right. Any questions about that? I know it's a confusing figure. The only thing I can offer, unless there are questions, is you'll see this again in another context. So the question is, people knew about metallic iron from meteorites, and they used them to make superior iron weapons. So here's an iron meteorite. The people that knew how to beat copper into a shape could work on iron and turn it into that. So this is an iron dagger that was discovered in King Tut's tomb that's older than the Iron Age, because the only way you could make it was to get an iron meteorite and just beat it. So people knew that iron was a thing and made very good weapons. They just didn't quite know how to do it. But eventually they figured it out. Yes, Clint?
I believe Michael Jackson had a song about that.
He did. He was very interested in the Iron Age. So the Iron Age is when iron started to be smelted from iron oxide, not just made from meteorites, because you can't really make very many anythings from meteorites. There's just not that enough of them around. But there's a lot of iron oxide, and that ability to get metallic iron out of iron oxide evolved sometime between 1200 and 600 BC. And the technology leap was again one of temperature. The temperature for melting iron oxide ranges from 1250 degrees centigrade to 1500 degrees centigrade. This is because iron oxide needs to be reduced to metallic iron, which occurs at 1250, while the melting point of pure iron is around 1538. So that's about 300 degrees hotter than you need to smelt copper oxide. And you could see that the technology that was being used to get those temperatures for the copper oxide, you just had to do more of that. So iron replaced bronze because once you know how to forge it, it's a lot easier to obtain iron ore than copper and tin ores, which you have to combine and make into bronze. And this technological leap, big surprise, was used most importantly for military purposes. Utilizing iron for weapons put arms in the hands of the masses for the first time and set off a series of large-scale movements of peoples that did not end for 2,000 years and that changed the face of Europe and Asia. Yes, Clint.
I understand that the end of the Iron Age was because bronze was a status item. For one thing, bronze was it depends on tin deposits, and so the end of the Bronze Age was the first economic collapse in at least the Western world, when all of a sudden, who needs this stuff? And so people who had a lot of bronze stuff just said, oh, to hell with it, and buried it.
Yeah. I don't know that story, but one can imagine that transition from the bronze technology to the iron technology was traumatic, like all of these transitions are. Now let's just talk about the hardness of materials. Now geologists are very well familiar with the Mohs hardness scale. Talc, gypsum, calcite, fluorite, apatite, feldspar. We teach that in the first class, and and that's a relative scale of hardness. Mohs was somebody that lived in the early 19th century, so but still it's very useful to teach to students about different properties of minerals. But in industry, we measure hardness in a different way. We've got instruments that measure the Vickers hardness in kilograms per square millimeter, going from 0 to 10,000, and you can see the Mohs hardness scale is pretty linear until you get to diamond, right? That's just off the charts. But hardness is a very important consideration when trying to make your military technology superior. Fundamentally, the question is, what makes a better sword, bronze or iron? So, I had always thought it was iron was made a better sword, but the answer is no, bronze actually makes better weapons than iron. Bronze has a Vickers hardness of around 300, whereas pure iron is closer to 100. So bronze is harder than iron. And if that was the only consideration, people would never have switched over to iron. So in battle, that means that iron weapons are harder to keep sharp and are more likely to bend. And there was a passage in Caesar's Gallic Wars where the barbarian warriors had to stop in mid-battle and straighten their bent iron swords in order to keep fighting. And the metallography of swords from that period suggests this was probably a true story. The Gaelic swords were typically made from pure iron, with very high ductility. That is, they're easily bent and would not have stood up well during a protracted fight. So the early iron weapons weren't very good, and this didn't really change until steel became widespread in the early Middle Ages. So given a choice between a well-made bronze spear and an iron spear, the author of this would probably choose to fight with the bronze. So the real reason for the shift from iron to bronze had more to do with economics. Copper and tin ores are rare, hard to obtain, and thus more expensive. And you want a big army if you want to win wars. And to arm a big army, you need iron. So that was the driver. All right, now we've basically taken advantage of the ores that are in the oxide zone, and we're still digging our pits because the kings and whatever still are having their wars, and they want more of whatever they're doing. But now we no longer have oxides. We get into this zone of sulfides, and so the sulfides, we'll be hearing about sulfides over and over and over again in this class. And it's got, most of them have a formula, some number of metal atoms to some number of sulfur atoms. So that's a sulfide. That's very different than sulfates. We'll talk about sulfates too, but sulfates have oxygen. Sulfides do not. So the sulfides is the zone below the water table where the ore has not had a chance to re-equilibrate with the surface environment. You could call it the exosphere if you wanted to, the outer part of the Earth, where groundwater and atmosphere interacts with rocks. The sulfide zone deposits have a high metal content, but they're harder to mine. You have to go deeper and below the water table. So that requires the technology to pump out or drain the water and proper ventilation. And then once you extract the sulfide ore, there's two stages. The first stage is roasting, which is eliminating sulfur by oxidation. So this is a typical equation for what is going on during roasting. 2 sulfides plus 2 oxygens goes to 2 sulfur dioxides and 2 copper oxides. And then you can reduce the copper oxide to copper metal the same way we just saw in that video, reducing it by interacting with carbon and carbon dioxide. So now let's talk about what all of this stuff did for civilization. It won't have escaped your notice that civilization really took off about the time that we started getting good with metals. And one of the most important was the use of metals for money. And I would say that money is the single most important invention of civilization because it drove innovation. So everybody has dreams of getting rich, which is making money, and that hasn't changed. So metals were key for the invention of portable money. So it's one thing to have money, it's another thing to be able to move it around, trade it, So before 600 BC, people used a variety of items for money. Cattle, that's a good thing of money. Grain, salt, animal skins, shells, gold, silver. These items were valued for their usefulness, perceived value, and widespread acceptance. So that made them suitable for facilitating trade. But you can imagine that the fact that skins they were useful to one people, but not the other one, shells likewise. But the invention of coins as standardized units of value marked a significant advance by offering a more convenient and universally accepted medium of exchange that's relatively easy to hide, right? If you have wealth, your first concern is to not lose it. So yes, Clint.
As I recall, it was the lawgiver of Sparta, Lycurgus, decided that they should have iron money so that nobody else would want it. It was for some weird reason. Yeah, I mean, it's Sparta, everything's weird.
Yeah, they were an interesting group of people. All right, so a coin is, as we know it, is a standardized unit of value. So here we've got what we think is one of the earliest coins. This is electrum, which is a mixture of gold and silver from Ephesus, which was in Western Turkey, from the 6th century BC, or I guess that'd be the 7th century BC. So on the left, we see a stag grazing and some words, some letters. And the right, there's some kind of incised punch. So, even if you're not from Western Turkey, you can weigh it and figure out what it's worth. Assuming that you believe it's what it said. That it's gold. Yes, Clint.
And this is where we, as geology teachers, get streak plates. You've heard of touchstones. And suppose somebody pays you in some of these yellow metal things, and you go, hey, I really trust you. Okay, now I'm going to rub it on this touchstone and see if I really trust you. Because if it isn't gold or electrum or whatever, it will have a different color streak.
Yeah. Yeah. So, geology basically, can date itself to the need to refine the science around mining, which is related to this stuff. So, and metals continued to be important as currency until the Western nations went off the gold and silver standards in 1971. So, let's talk a little bit briefly about steel. Why is steel better than iron? It's generally preferred because of its superior strength, durability, and versatility. It is enhanced properties are due to the addition of carbon, other alloy metals. Began to be made about 4,000 years ago, dating back to the 13th century BC. And it's believed that steel was discovered accidentally when iron was left in a coal furnace containing high carbon levels, resulting in a stronger, harder, more durable metal. So when did the modern steel industry begin? This began in 1856 with the invention of the Bessemer process. So basically, you could mass produce steel by melting down molten iron, oxidizing it, and removing impurities that included silicon. I'm not sure what MS is, and carbon, which would escape the molten iron as gas, or would solidify on top as slag. And it completely revolutionized steel production by allowing rapid and inexpensive mass production of high quality steel. Prior to this, you couldn't do it. So the growth of the cities in the late 19th century, skyscrapers and all of those things, was largely reflecting the availability and cheapness of steel, which could be used for structure. And bridges, they didn't have to make bridges out of wood anymore. They could make it out of steel. So I just basically said that. The first, just maybe worth mentioning, the first steel framed skyscraper, the Home Insurance Building in Chicago, was completed in 1885, standing an astronomical 10 stories high. And then the Eiffel Tower was built not long after that. So that was a very experimental technology, building with steel back then. All right, so iron is always the main element in steel, but there's other elements that you can add to generate steels with different properties. So stainless steel typically contains 18% chromium, which allows it to better resist rusting and corrosion. There's four main types of steel. Carbon steel, with up to 2.5% carbon, has enhanced strength. Alloy steel combines carbon steel with elements such as titanium, copper, chromium, etc., for specific material properties. Stainless steel, we just mentioned, is to resist corrosion. And tool steel is an alloy with enhanced hardness, resistance to abrasion, and shape retention. So, this is material science stuff. Now, metals were important for colonialism in two ways, both coming and going. So coming, the role of guns and steel in conquering the Native American civilizations, especially the Aztecs and the Incas, is famous. Just a handful of Spaniards with their guns, steel swords, and of course the horses. That was also a big part of it. Were able to subjugate these two monstrous, large civilizations. And then once they were there in Mexico and Peru, they quickly realized that there were a lot of metals there that they could get, and they did get. And there were some poetic moments, like Pizarro's brother. Pizarro was the conqueror of the Incas, and here we have the Spaniards were so hungry for gold that the Incas were just puzzled by it. But there's the famous story is Pizarro's brother was killed by having molten gold poured down his throat. So at least he got remembered in history. All right, so colonialization led to global mining activities. There is definitely a history of exploitation behind mining. There's no question about it. But here we are today, and we need these things. We can lament the colonial exploitations, and there are controversies about mining in other countries. A lot of what's happening in the United States now is the recognition that we rely too much on other countries for our mineral needs, and that's neither just nor politically appropriate. If we're, taking advantage of other people, at the same time we're exposing ourselves to international political pressure. Those are two reasons to find our own deposits in the United States as much as we can. So, how many pounds of minerals are required by the average US and Canadian citizen in a year? I do like the word citizen person. So 275 pounds of iron ore, 168 pounds of phosphate. That's fertilizer mostly for plants. 35 pounds of soda ash, 34 pounds of aluminum, 12 pounds of copper, 11 pounds of lead, 6 pounds of zinc, 5 pounds of manganese, a tenth of a pound of uranium, and 25 pounds of other metals. So that's we need metals. We rely on metals, and we take them for granted. So here's metal in the average car. So 62% iron and steel, 10% aluminum, 2% copper and brass, and then a bunch of other stuff too. And these, this diagram from the USGS is just sort of showing all of the different things that use minerals and metals in our homes. Now, this shows a snapshot of what we mine in a year. So down the left, we have iron ore, and then we've got aluminum, manganese, chromium, zircon, copper, zinc, titanium, lead, nickel, a lot of other things. But you can see that, the vast preponderance of what we're mining is iron ore, and then second is aluminum, and third is manganese, and then so far down. We're basically using the entire periodic table, but parts of it we're using a lot more of than other. Now, one of the realities is we can only go so deep in the earth to get this stuff. These are the top deepest mines from Wikipedia. And the Mponeng gold mine in South Africa is the record holder, 4 kilometers deep. That's, you can see that most of these, every one of these deep mines is for gold. And, one can imagine with the present rise in the value of gold that they're going to be trying to figure out how to get deeper and deeper, but they're pretty much near the limit. 4 kilometers, it's going to be tough to go any deeper. And that's a absolutely trivial part of the earth. It's the outer 0.03% of the earth. And even from the point of view of the continental crust, which is typically 40 kilometers thick, we can only access the top 10%. But so we've got some structural limitations that have to be accepted and planned for. So mining is now mostly done by global companies. The top mining companies of the world are generally considered to be BHP, Rio Tinto, and the Chinese Shenhua Energy. Glencore is the world's largest mining company by revenue. So these are the companies that control most of the mines. So how do companies and investors think about the economics of deposits? Yes, Glenn.
I didn't see a Sarco in there anywhere. What happened to the old American stealing and robbing company?
I don't know. So, we think about a deposit in terms of what it contains. So there's terms that are used that I find confusing. In North America, we talk about mineral resources and mineral reserves. In other parts of the world, they talk about ore reserves. These are not synonymous. Mineral resources and mineral reserves are not. They refer to two distinct types of estimates that mining professionals, investors use to make decisions. So the distinction primarily concerns potential economic value, which is a resource, as opposed to the present economic value, which is reserves. So given that it takes many years to bring a prospect into production, typically 10 times the amount of time required for an oil well, the projections of commodity prices are also critical. So here we've got a sketch showing the difference between the extent of mineralization, the extent of the resource, and the extent of the reserves. So we were looking at a map view. It looks like it's 40 or 50 kilometers across, and it's a huge area of mineralization. But when the company's basically trying to figure out their business plan for this deposit, they've got to focus on the reserves and maybe the resource, but the most important thing are the reserves. So those little holes there are intended to be drill holes or other kinds of sampling sites, so that the company can get a true estimate of the two-dimensional configuration of the zone. So you can see that there's only a few drill holes in the larger mineralized zone, but there's a lot more in the resource and in the reserve. Those are much more important from the point of view of convincing banks and investors to invest. Okay? And resources can become reserves and vice versa, depending on the cost of extraction relative to its value. So, for example, gold price has basically doubled in the last few years. So we can expect that the reserves have increased considerably because deposits that previously, up until a few years ago, were not economic, now are. So that moves them from the resource into the reserve category. So how do we estimate reserves and resources for a deposit, we drill. And so what you can see here is the kinds of maps and cross section. That's a map. These are cross sections showing drill holes that go in. So here we're looking at that blue, purplish blue is limestone. That green is a skarn, which is a kind of a mineral deposit. And then this pink is a granite, which was a heat source that, we'll talk about how these zones of mineralization often happen between intrusive bodies and limestones. So this is something of the map view. And then this is showing the drill hole sort of surface projection of these things, because they're typically inclined like that. And then here you can see, I can't really read what the scale means, but it's basically giving information about the abundance of the element of interest in the borehole. And the mining geologist and the engineers are going to take that information and come up with as accurate a model for the extent of mineralization as possible. Now, this is how you do this is a course in its own right, which you're not going to get from this course, but it's a key part of figuring out the economics of these deposits. Now, let's watch a video. We like that.
The main objective with core drilling is to produce a core sample of high quality. The core sample is used to check the mineral content and/or the quality of the rock or the soil. Core drilling is a rotary cutting drilling method. A ring-shaped drill bit armed with cutting tools, for instance diamonds or tungsten carbide, is forced against the rock surface and is rotated clockwise at a high speed. A round bar, a so-called core sample, is cut out of the rock or out of the soil. The most common areas of application for core drilling are exploration drilling, definition or infill drilling in underground mines, site investigation for rock mechanics purposes, and site investigation for soil mechanics purposes. In exploration drilling, the exploration geologist examines the core sample to see if the rock mass contains any valuable mineralization. In definition or infill drilling, the mining geologist drills in order to follow the ore boundaries and to examine the ore concentration in the mine for production planning purposes. In rock mechanics, the rock mechanics engineer analyzes the mechanical and hydrological properties of the rock mass to determine whether it is possible to construct, for instance, a tunnel in this rock mass. In soil mechanics, the geotechnical engineer studies the core sample in order to obtain information on whether the soil layers must be reinforced and sealed to withstand the stresses of a planned construction.
We are in the area of the Core 6 min file out here at the Star of the West property. And what we're going to do is we're going to pop a backpack drill hole up into a little showing up here. Hopefully intercept some mineralization down below. You do have a lens underneath here. Some massive chalcopyrite, some sphalerite, galena, pyrite and magnetite in there. So what we want to do is just see what we intercept. This is just a kind of a test hole, the first one we've done on this property. Let's get to her. So there's a bit of massive sulfide mineralization in this area. Along here, some surface stuff that we're just going to start our hole into right here. We have the Kawasaki motor here. We got our drill rods, 3 to start, and our water. So let's get to drilling. We got a little bit left in this drill bit, so we'll use this one till it conks out. So we got 5-gallon water tanks here that we have to fill up intermittently. You hand pump this, so you keep it all nice and wet.
Grab it.
We are good to go for the next one. We did get some massive sulfides though in the first meter. Pretty much the entire first meter here is massive sulfides. And then you hit volcanics right after this. You got a little bit of sulfides in there. A little bit of sulfides there, and then you have volcanics and rubbly core, and you have a patch of sulfides right there. I don't know if you can see that. Just a band. And then nothing. So what we want to do is we want to bag these in 1 meter intervals. Specifically, what we're interested in is the first meter, getting a reading on all these massive sulfides.
You know, some of these rocks are amazingly complex. You know, the mineralization process is in no way simple. So here we've got an example of a porphyry copper mineralization. So that's called stockwork, and that those quartz veins, those lightish gray things, are permeating this porphyritic igneous rock, and they're sort of stained with potassium feldspar alteration around their margins. So this is described as supergene copper enrichment with copper oxides overprinting potassic altered quartz diorite porphyry. So there's a lot of jargon in there, and you'll be hearing more of that in the future. But you know, many of these deposits are extremely complex from a geological perspective. So just this shows another example of, you know, how you would go after evaluating a prospect, you know, that you saw at the surface. Oh, it looks like there's some, you're walking around, you go, oh, it looks like there's some mineralization come in with, you know, there's 3 drill holes, 4 drill holes, another one back the other way. And then the, you know, what you find where the zones of copper are, that's got 0.2% copper and half a gram per ton of gold. So, you know, these are all things that have to be figured out before you can go to the bank or the investors to be taken seriously. Now, as we were talking about reserves and resources, this is the price of gold. So from 2015, it was $1,200 an ounce to last time I looked, you know, was in May, close to 3,500. You know, are there more gold reserves today than in 2015? Yes, because, you know, a deposit that was cost $1,500 an ounce to produce would not have been considered to be a reserve in 2015, but it would certainly be considered to be a reserve today. Likewise, $2,000 an ounce, $2,500 an ounce, even $3,000 an ounce. You know, there's a lot more. Now, are there more uranium reserves today than in 2007? And the answer is no, because the price of uranium is lower today than it was in 2007, right? There's in neither case has the amount of gold or the amount of uranium changed. Nothing has changed in terms of what exists out there. What's changed is what we see is economic to go after. So, it's important to stress that getting the metal-bearing minerals out of the ground is only the first part of the process. There is the process of extraction, as geologists, we're sort of fixated on. The process of obtaining minerals from the Earth's crust, that's an awful lot of what this course is going to be about, not the mechanics of extracting it, but how it's found, which is obviously going to dictate how you get it. And then the part we won't talk nearly as much about, but is clearly an important thing, is processing. You've got to refine the ore for the not only to generate the pure metal, but also to prepare it for other industries. So mining and refining operations are spread across the globe, with the major centers in regions that are rich in mineral resources. Yes, Clint.
And as I'm sure you'll get into, this goes hand in hand with energy availability and price.
Yes. This is, as you can see from that primitive video about smelting copper, energy is a huge part of processing. And then global trade.
Also looking really buff while operating some bellows.
Yeah. One suspects that's not his day job. Global trade, that, mineral products it's a commodity. It's going to be traded internationally. And then finally, manufacturing, the things that we actually use. That's a whole nother field. So, but we're going to focus on this course on an extraction, and it's particularly the kinds of deposits there are more than actually how we extract them, although we will touch on that from time to time. And that completes the first lecture.